Okay, so let's start with this question number 4. You have skipped out. Let us take this question number 4. Two small spherical conductors B and C having equal radii and carrying equal charges on them repel each other with a force F when kept apart at some distance. A third spherical conductor A having same radius that of B but uncharged is brought in contact with B, then brought in contact with C, and finally removed away from both the new force between B and C. So the question is that there is two spheres and third sphere is brought in contact individually one after the another. Then forces between B and C, how it is changing. Basically, charges are changing and force is proportional to the product of charge. Distance is not changing. So only thing that you need to figure out is what is the initial charge and what is the final charge. That's all. After that, finish. So let us say this is B and this is C, correct? B and C is that two small identical charges carry equal charges. Let us say charge here is Q, right? And another third is you are bringing in contact. So third you are touching first B and C. Third you are touching it. So after you touch this, then B will have how much? Half charge. Half, right? Because they are identical, so it will become half now. Now B has become half, correct? And A has also got half now. A has also got half, correct? Because when you touch identical, equal charges got distributed, half it become. Then they are saying A is again touch with C. Now C has how much charge? C has charge Q and A has Q by 2. So how much is total charge? Total charge of the system A and C is Q plus Q by 2. That means it is 3Q by 2. That means total charge of A and C is 3Q by 2. Then half is again getting divided, half. So now C will have half of this, that means 3Q by 4, and A will also have same. A will also, right, correct. A will also have same. A will also have same. Correct. Now, what is the force between B and C? B and C we have to consider now. B and C you have to check. So B and C, how much is the charges? Previously, how much the charges? Force was F. Force was proportional to product of charge Q into Q. Now let us say force has become F dash, product of charge between B and C, Q by 2 and 3Q by 4. So do that, Q by 2 into 3Q by 4. How much it becomes? 3 by 8 become. So F dash become 3 by 8 of Q square. Then you take ratio, take the ratio. So you can get very easily, because F dash by F ratio becomes 3 by 8. That's all. So F dash become 3 by 8 of F. There was not much calculation involved, not much calculation, right? 3 by 8. So that's all. Fourth option. Then next, let us go next. Then next is correct. Next you have got correct. Sixth question you have left out. Sixth question. Question number 6 again. In the following figure, point A is at a distance L away from a point Q. Okay, L distance away. Okay, point B is at the distance 4L from Q. What is the ratio of electric field at B to that of? This is a quite easy question. Why you left out? I don't know, but but it is a very easy question. They are saying that point A is there. This point is L distance from charge. This is charge and this is L distance. Then they are saying another point B is there. Point B which is 4L distance from here. 4L, and they are asking ratio of the field here and here. So here field will be what? Field, here field will be, field at B will be kq by r square. R square means 4L whole square, and here field will be kq by r square means L square. That's all. Over ratio you have to take, so EB divided by EA. This is field at A. So what is the ratio? It is inversely proportional to, right? That means 1 by 16. 1 by 16, direct answer will be there. 1 is to 16. No calculation in that. Nothing calculation. Why you left it? Tell me. This is a very easy question. Hmm? Easy question we should do. This question comes under easy question. We should not leave it. Okay. Next. Let us go to question number 7. 7 also left out. Question number 7. What is that? Okay, rigid electric dipole is free to move in the electric field represented by. So some electric field is represented like this, like this. Some field lines are represented like this. Okay, field lines are represented, and you know that wherever field lines are closer, field strength is more. Wherever field lines are away, field strength is less. So definitely, in this region, field is more. Here, field is less. Okay. Now they are keeping a dielectric. They are keeping a dielectric here, like this. Dipole. So minus q plus q. There is a dipole kept here. Question is what? Okay, it is released. Dipole is released. Which of the following phrases most accurately describe the initial motion of dipole if it is released from rest in this position zone? It moves to the left. So we need to see first of all forces acting on the dipole. Forces acting because the field is not uniform. Field is not uniform. Fields are different. So different forces will act. So if you see here at this point, so minus charge is there. Minus charge means what? It will go in the direction of field. So field direction is that way. So this will experience a force. Is it a positive charge or negative charge? Negative charge. Positive charge will go in the direction of field, right? Negative charge will go opposite of that. So positive charge, this one will go in this direction. And here let us say force is charge into field E. Let us say E1. Here it will go opposite of that. So it will experience here Q into E. E to you, let us write magnitude. I am writing magnitude, right? But you can see the direction this way, that way. Now which field is more? Which field is more? Field here is more, so E2 is larger. Field here is less, E1 will be smaller. So this force is definitely going to be larger. You may draw this field little bit bigger. This force little bit bigger you can draw. So this force will be very large, this force will be small. So resultant force will be towards left side. That means this body will move towards left side. Definitely A moves to the left first itself is correct. Okay, we don't have to go for more, leave it. That's the right answer. Let's move next. Next question is again unattempted, question number 8. Let us go for question number 8. Question number 8. Equilateral, there is a triangle, identical point charges at the vertex. Okay, length of each side is d. Okay, determine the magnitude and direction of total electrostatic force on the charge at the top. Very easy question. I don't know why you have left it. I think you have already practiced this type of questions. Forces, this is from the topic of forces. D are the distance, right? We need to calculate force on top of the triangle. That means this one. Where is the force going? Okay, so calculate the force. This force, you know, k cube by r square. This also is going to be same, right? Are they going to attract or repel? I think they are similar, so they will repel. Direction will be opposite. Draw direction properly. Direction is opposite, so this force will be like this force will be like this. Both forces same magnitude, k q square by distance square. This is the force. And equilateral triangle, so this angle is same as 60 degree. Then you just find out resultant force. Suppose two forces are at equal angle, theta, then the resultant force becomes what? 2f cos theta by 2. This is a very basic idea of resultant force. 2f cos theta by 2. Simply apply that. So net force is going to be 2 into f is k q square by d square. Cos of 30 degree root 3 by 2. 2 get cancelled. Now if you want in terms of 1 by 4 pi epsilon, write it 1 by 4 pi epsilon naught. This becomes root 3. You write it here. Okay, q square by d square. This is the force, right? Q square root 3 4 pi epsilon d square. Which direction it is going? Direction, you know, it will be going exactly in this symmetrical manner. It will be going upward like this. It will be going upward. So you know this is the magnitude of force, but it will be acting in this direction, upward. So which direction? Which is the correct answer? Option A. First option itself correct. No calculation much. These questions are very easy question. You could not have skipped it. Okay. Let's go to the next question. Number 9 is the mistake happened. Let us go to question number 9. Question number 9. Okay, a conducting sphere carries a net charge of -6. Okay, the sphere is located at the center of a conducting spherical cell that carries a. So there are two things. One is a cell, one is a sphere. So one is like this, right, and another is a cell. Let me draw cell like this. This is a cell. Cell means it is like a completely hollow. This is completely solid. So they have given that net charge here is -6. This charge on this is -6 microcoulomb. Correct? Okay. Located at the center of a conducting cell that carries. The cell has a charge of +2 microcoulomb. +2, and you should know that minus charges here are distributed over the surface. Here the plus charge will be distributed over the surface. This thing we have to quickly process, that this is how this is distributed. You don't have to draw this, you have to do calculation, but I am drawing it so things are clear here. Okay, then determine the excess charge on the outer surface of the spherical cell. Outer surface, what is total charge? Remember, this is the total charge on this. Now let us do the induction. Induction means how much is inside. Note that here on the outer surface, of inner, there will be only charge, whatever it is. There cannot be any charge in the inner surface of the conductor, because this is a solid conductor. Even if it is a hollow conductor, there cannot be any charge inner surface. Okay, on the inner body, inner surface, there won't be charge. So charge on the inner body is only on the outer surface. So here this -6 microcoulomb will be on the outer surface. Now due to induction, you have to write this as +6, because you know in induction plus minus happen. So if this is minus, so here will be +6. On the inner surface of this cell, we will have +6 microcoulomb. Now this is +6, and what happens that the total charge here is +2. So this is +6. What should be the remaining charge? What should be the remaining charge? You can say that if +6 has happened, so this side will become -6, because total charge due to induction must be 0, because if you touch, only charges will transfer. So here induction must be 0 charge, it will give. So +6 -6. But now if you see on this body, there is +2, and this is due to induction -6. So -6 plus 2 will become how much? -6 plus 2 will become -4. So this must be the total charge on the outer surface of the cell. This is simple process of induction. Okay, so the correct answer is first, -4 microcoulomb. Clear? Are you clear about this? Yes, Satres. Are you clear? Okay, then next last question. Question number 10. Question number 10. A charge of 10 power -6 coulomb of mass, this is free to move when released at a point distance a from the fixed charge. Okay, so there is a fixed charge capital Q, and from that fixed charge at a distance of a, there is a small charge q is released. This charge is fixed charge. This charge is free to move. So release means due to repulsion it will go away. After some time, the distance between them changes to b. Initially distance was a, now distance has become b. They have given the value of a as 1 meter and b as 10 meter. Okay, and capital Q charge is also given as 10 to the power -3 coulomb, and small charge value is 10 to the power -6 coulomb. Right, all these things are given, and the mass of this particle, this is also given as 2 gram. 2 into 10 to the power -3 kg. Right, gram I have converted to kg. Now question is, what is the speed? When it reaches here, what is the speed? With this type of question we discuss in the class. Okay, but let us say you have forgotten concept of potential, still you can do by work energy theorem. Remember, we discussed this a lot in the class. Work energy theorem, how can you apply? Then work done by this electric force, work done by electric force is change of kinetic energy. So final half mv square, initial kinetic energy 0. Work done is integration of electric force into the displacement dx. So electric force is acting like this, right? Electric force is acting like this, and dx displacement is happening in this direction. Apply the formula for force, 1 by 4 pi or small k q into q by distance. Let us say distance is x square dx, and this is half mv square over. Then you do this integration, so k q comes out. Integration of 1 by x square is minus 1 by x, and it is going from a to b. That is what is half mv square. So this becomes kqqq minus 1 by b minus minus plus. So 1 by a minus 1 by b is equal to half mv square. Now if you want, you can substitute values. I'll do calculation this side. Substitute. K is how much? 9 into 10 to the power 9. Capital Q and small q multiply. So 10 power minus 3, 10 power minus 6. So 10 to the power minus 9. Product of charges has become that 1 by A, 1 by B, 1 by A, 1 by 1 minus 1 by B, 1 by 9, sorry, 1 by 10. This has become equal to how much? 1 by 2. What is mass? 2 into 10 to the power minus 3 into V square. Now you solve out that. This is not a big deal, right? We can easily solve it. How much it will become? 1 minus this become 9 by 10, correct? This is 9, this gone, so this become 9 by 10. This 2 also gone, 10 minus 3, and this is v square. So from here 9 into 9 81, and here this bring this side, how much it is? How much? 10 to 1 by 1000, 100 will come, under root of that. That means 90 meter per second. Easy calculation, direct answer, not much tough calculation. Definitely by practice you can 1 minute, you can do within 1 minute. Okay, so first option, that's all. So tell me, what are the doubts you face? Because I want that you should improve. Where are you lagging in this? Did you give any other test? Only first and second test you have given. We have other test also, DPP3, DPP4, DPP5, DPP6. We have made so many papers. Up to 6 we have made. So you should finish those. So tell me, like, what are the doubts? How can you improve that? Is it the lack of practice or what? Hmm. You have to improve the speed. Really, you are now in a race. You are in a race. You are not alone doing. There are so many people who will be sitting in the exam with you. Lakhs of people. You are in a race. So in a race, you have to recognize that you have to run fast. You have to do it fast. So you need to improve your speed. Second is that easy question you cannot leave. Okay, easy question, you see what you left are very easy questions. Of course, suppose you leave this, it's okay because this may take some time. But easy question, half an hour. How did you give for half an hour? How much time you give for this test? Hmm? And then half an hour means half an hour means you can do more, because one question cannot take more than 3 minutes. 3 minutes is maximum side, I am saying. First I am giving you 3 minutes every question, then gradually I will improve time, I told, right? So you need to first go through that 10 question. 30 minutes is more than sufficient. You must attempt all these questions. So speed you need to definitely improve. Why is your speed slow? Tell me. Are you not solving questions? Then okay, when you are solving question worksheet, are you taking more time? Hmm. See that's what daily you must practice it. Daily you must practice 20-25 question at least, and maybe it will take more time initially, but make it a habit of practicing question, because physics will not be like easy questions just by reading theoretical questions you will give. No, many people are expecting like that, but every question will have calculations. Sometime you have to read, then you have to process it, then you have to think which formula I have to use, then you have to do calculations. So many steps will be there in every question, and you have to really fast, and this ability, this skill you have to build up, then only you can do question fast. Okay, so how much we have covered? If you see theory, how much I think potentials we have covered. Potentials we have covered, right? hmm. Last class theory, how much we have covered? Last to last class, because last class only problems we discuss. Before that, uniformly charged ring, we have discussed about electric field, maximum potential also we calculated, right? Okay, then uniformly charged disk field we calculated, then potential also we have calculated. Okay. Hmm. Then let us go further. Let us go today on so same way we will continue this derivation, right? So we have done for ring, we have done for disk. Ring and disk is over. Then we will go for hemispherical cell. Hemispherical cell. Electric field, electric field and potential due to a hemispherical cell. Okay, so let us take this hemispherical cell means like this cell is there. Okay, you can join it like this also, but it is cell. Cell means charges are present everywhere here. Very thin cell it is. Okay, charges are present. Let us consider some charges are present over this thin cell. Okay, so this is a thin hemispherical cell and charges are present. I have drawn only on the line, but don't think it is only on the line. It is everywhere on the surface of this. Okay, here also I can draw, but the diagram will become dirty. To make it clean, look clean, I have just drawn like this. But charges are on the surface of this, because this is a hemispherical surface. Okay, so we want to calculate what? We want to calculate electric field. Where do we want to calculate? We want to calculate at the center. At the center. What is the field at the center? Oh, so to calculate field, after that potential also will calculate. So what we need to do is we need to consider a small element here like this, which is like a ring element. Okay, so we can cut it like slice you make this small slice which you will make. This is like a ring, so this is a ring element. This is a ring element like this, and it is made up of so many such rings, right? And note that this, suppose this distance from here, uh, the distance of the center of this ring from the center of this base, right? some distance y you can choose, and this radius is small r, and this r will be variable because this can change, and this is capital R. Let us take this as capital R. Okay. So now we want to find out, now this ring is like a small element, right? This ring is like a small element. Separately also I will draw. This ring is a small element. Now this ring has some charge. How much charge is there? Charge is dq. Dq is the charge. So what is the charge dq? Dq is equal to sigma into dA. dA is what? dA is the area of this element. What will be that area? How do we calculate that area? That is very, very important. For that, you have to note that at this point O, it is making some angle. This length is making some angle theta or d theta here. And from this vertical position, you can consider this as theta, right? So theta value can go from 0 to 90 degree, right? Theta can go from 0 to 90 degree. How will you consider this area of this? Area, how will you consider? So this length is important here. This length is dl, let us say this length is dl. So this dl will be r d theta. Dl will be r d theta. But what will be the small area? The small area will be this length is small r, right? This radius is, so 2 pi r into dl. 2 pi r is the circumference into the thickness. Thickness you cannot say that thickness is dr. Thickness is dl because the thickness lies in this direction. Okay, remember thickness will be lying in this direction. Okay, so then let us try to convert. Also note that this is capital R, so small r can be written as r sine theta. We can write this small r as capital R sine theta. So dA can be written as 2 pi small r is capital R sine theta, and dl is r d theta. So from here dA you got as 2 pi r square sine theta d theta. Right, you got this. Now once you got this area, this charge you can now substitute. So sigma into dA, which is 2 pi r square sine theta d theta. Okay, now you got the charge. Now you remember the electric field on the axis. I hope you remember that electric field on the axis. Do you remember that? Electric field on the axis, what is the formula? So this is like a small ring, its axis and its charge is, so directly write the field due to that. Directly we are writing field due to this. Okay, I am writing directly field due to this. You know that field will go in this manner, so field here will be going in this manner. Direct formula, now I am going to use it. So dE, what is formula for dE? K into charge dq, kq, k kq into this distance. Distance is how much? Y. Kqy by this is square, this cube, not square, cube, r cube. This r is root under y square plus r square power 3 by 2. So directly we can write this as r cube. Okay, now let us try to simplify that. We have to integrate this. So first you simplify this k dq. Now you put it sigma 2 pi r square into sine theta d theta. Y can also be written as, because this angle is theta, so y can also be written as r cos theta. So y can be written as r cos theta divided by r cube. Now try to simplify this. So this electric field we will integrate dE. This is dE. So when you integrate, what will happen? Note that r cube terms is going to get cancelled. So constant term take out, 2 pi sigma k. 2 pi sigma k has come out. We have only remaining as sine theta cos theta. Sine theta cos theta d theta. And I will say that better you take these two also inside. Right? Take these two also inside. Why? Why I am saying that? Sigma pi k. Keep 2 also inside, because 2 sin theta cos theta becomes sin 2 theta. Very easy to understand, because this sigma pi k will become sin 2 theta now. Sin 2 theta now integrate. And angle is going from 0 to 90 degree. You should remember 0 to pi by 2. Pi by 2 means 90 degree. Okay, now integrate sine. So sigma pi k, sine integration becomes minus cos 2 theta. And note that the coefficient gets divided. Okay, and we have to take from 0 to pi by 2. 0 to pi by 2. Let us now substitute that. So electric field becomes sigma pi k. 2 also take out. Then put minus. So this become minus cos 2 pi by 2 means cos of pi minus plus cos of 0. And cos of pi itself is minus 1. So minus plus 1, 1 plus 1, 2, 2, 2 also get cancelled. So you are getting this formula sigma pi k. Very, very important formula. Now we have to record in mind this, what it is, that electric field at the center becomes sigma pi k. If you want, let us simplify. Sigma pi k can be written as 1 by 4 pi epsilon naught. So now pi get cancelled. So you get the answer as sigma by 4 epsilon naught. Okay. So remember that. So electric field at the center of the hemisphere, it is not a semicircle. Okay. Hemisphere, center of the hemisphere, electric field is going to act in downward direction if it is positive. Otherwise, if it is negative, it will act towards that. So this is sigma by 4 epsilon naught. Are you clear about this? Tell me. Hmm. So this is the derivation of electric field at the center of a hemisphere which is uniformly charged. Sigma is the charge density of the surface charge, right? That is the important result. We should remember that. Okay, then what? Then field is over potential. Let us calculate potential. Exactly in the same way, we can try to calculate potential. Calculate potential. Calculate potential. Now potential we want. So again same way. Go to the same approach. Same approach. Everything is going to be same. You have made a ring element here. All calculations are same. I am not going to repeat much calculation now here. At the center we want potential. So we know that this radius is capital R, this radius is small r, this is y. So potential at this charge is dq. Dq we have already solved previously. What is this? So what we have solved dq? Let us write that. Dq we have solved here. Where we have solved dq? Dq we have solved sigma 2 pi r square sin theta d theta. Same thing. Okay. Sigma pi square, sigma 2 pi r square sin theta d theta, right? Is it correct? Sigma 2 pi r square, is it correct? Sigma 2 pi r square sin theta d theta. Yes, this is what? This is dq. Already I am not repeating again the same calculation. Okay, this dq we have already calculated, right? Now potential here, remember potential formula is, what is potential due to ring on the axis? Small potential k q by r, q, and this radius you have to write. So k q by this radius, this radius. Okay, because every point on the ring is equidistant from the axis. Okay, k q by r. Okay, so let us do calculation. K is anyway constant. Dq you substitute sigma 2 pi r square sin theta d theta divided by this capital R. Over now, over. Very easy calculation. R is going away. Constant terms comes out. So total potential is integration of dV. Do that. K sigma 2 pi r comes out. You have to just integrate sin theta d theta. integrate that. So k sigma 2 pi r, sine integration becomes again minus cos, and cos goes from again same 0 to 90 degree, 0 to 90 degree, pi by 2, 0 to 90 degree. So what will be the result now? K sigma 2 pi r cos 90 becomes 0, minus plus cos 0 is 1. So this simply become k, also now you write k is 1 by 4 pi epsilon naught sigma 2 pi r. So here what happens, things will get cancelled, and sigma 2 pi got cancelled. So sigma r by 2 epsilon naught. Very important result. Potential at the center of a hemisphere is sigma r by 2 epsilon naught. Clear? Are you clear about this? Yes. So potential is over and field at the center is over. That's all. For a complete sphere, they will not ask, because for a complete spherical cell, we already know field is 0 and potential is constant, right? Okay, then what can be done then? Further, I think this. What about solid if they give solid? What about solid? Can we do the calculation for solid as well? Definitely we can do. Why not? Solid means it's like a volume distribution of charges will be there. Okay, let us try that. Hmm. Hmm. But also note that for suppose they have given complete, then what? Suppose they have given complete cell, complete spherical cell, then what? They may ask then inside potential, on the surface potential, outside potential, because field result we know from Gauss law. Gauss law we know that field is inside is 0 and other things, right? Gauss law have we covered or not? I am not sure. Have we covered Gauss law? Gauss law we have covered, na? Gauss law if we covered, how much we have covered Gauss law? Did we cover the derivations? I think last to last might have been. Let me just check. Are you downloading the files of this question, which link I am sending? This link after the class which I shared, are you downloading all those? Please download it as PDF, otherwise they will remove that. It is on the cloud data, because I am not able to access some of the previous links. I think the XML does not appear. They have removed or not? Yeah, something have been removed. So Gauss law, how much we have covered? Do you remember that? Electric flux we have discussed or not? I think we have covered electric field related with everything else. Okay, but we will see the applications of that. Okay, I think we have proved that, but now let us see the applications of that. We want to calculate the field and potential. So briefly I will review that. So let us take a complete or a spherical cell, a spherical cell, or a solid spherical conductor. Solid spherical conductor. So either you take a spherical cell or a conductor. What is important is that the charges are distributed over the surface. Okay, so let us consider a very thin spherical cell, or you can assume that it is a solid. So one thing is sure, that charges are only present on the surface of this conductor. Charges are present on the outer surface. Charges are present on the outer surface. If anything is inside, then inner surface also charge can be present. But right now there is nothing inside, so only charges are present on the outer surface. Okay, so now what we want to find field here, and you want to find field somewhere here. So we are taking some points. Let us say some point is here. Okay, and this is the center. This is the distance of r. So what do we do? If you remember, we have to make what? Gaussian surface, right? So let us make this Gaussian surface. Let us call this Gaussian surface. Gaussian surface. Gaussian surface. If you consider this as the Gaussian surface, then what happens is that, what is the Gauss law? Gauss law says that the net flux is equal to charge inside by epsilon naught. This is what is Gauss law, net flux, right? So what is net electric flux? It is integration of E dot dA. E dot dA, charge inside. But here what is there? There is no charge inside, all the charges are outside. So for this point P, there is no charge inside, so this becomes 0. So from here you can write E into area, integration of area is equal to 0. So definitely here field is going to give us 0. That's how we get this concept that field inside a spherical cell or inside a solid conductor, field is going to be 0. Right? That's a very important result. We got field 0. Then what else? Okay, 4 points outside. 4 points outside, again we have to construct a Gaussian surface like this. This is a Gaussian surface. This is again Gaussian surface. Gaussian surface. Now in this Gaussian surface, you want to find out what? We want to find out what is the again field at this point. Any point on this field we want, and this distance is r. Remember, for this is the case when r is less than capital R. Okay. What happens when r is greater than capital R? Capital R is the radius of this sphere. Okay, so when you are going for points outside this sphere, what happens now? Now total charge is inside. Total charge is inside. Okay, so when you are using Gauss law, this integration of E dot dA is total charge is inside divided by epsilon naught. Okay, now E is coming outside here, and integration of dA you have to do, and this is charge by epsilon naught. So dA integration area of this sphere will be 4 pi r square is equal to q by epsilon naught. That is why electric field comes as 1 by 4 pi epsilon naught q by r square, which we already know it is like k q by r square. This is just like a point charge, like a point charge, like a point charge. Are you following this? Yes. So for points outside the cell, this whole charge on this cell or whole charge on this sphere behaves as if the charge is like a point charge at the center. That already we know that. But now we have proved it using Gauss law. Okay, so this is first important. So field results already we have written long back, and Gauss law we have already proved. But what is new is potential calculation, and field graph also you can draw here. The graph of field also we have drawn previously also, but let us again draw it. Field graph is like this. Field graph is like this. So field is 0 here up to the surface, and from the surface outward it goes like this. So this is discontinuity. So the graph is a discontinuous graph. Discontinuity. So there is discontinuity because just before the surface the field value is 0, and just after the surface field value is kq by r square. Kq by r square. This is r is equal to capital R. Okay. So there is a discontinuity at the surface. If they ask what is the field at the surface, because field at the surface itself is not defined. Okay, because at the surface r equal to capital R is not defined, it is discontinuous. But if they just ask before the surface it is 0. After the surface, just after the surface, kq by r square. Okay, this formula we should remember. Now what about the potential? We want to calculate the potential also. How does potential graph will look like? We need to derive it, and for doing that derivation we must know the concept of potential energy and all that. Okay, so let us derive the potential due to a spherical cell or a spherical conductor. Solid spherical conductor. So let us say that total charge given to this conductor is capital Q. Capital Q is the charge given. Radius of this is R. We want to find potential somewhere here. But we know that the field is going to be 0 already. We know that field is going to be 0. But how to calculate potential? So here field is 0 at this point, and if you take any point outside at a distance of r, so their field is given as kq by r square. Okay, now let us recall what is the formula for potential. What is relationship between potential and field? You remember the relation between potential and field? Yes. There is a differential equation, right? Differential equation. What is that? Yes, right. E is equal to minus dv by dr. Good. That is what it is. So we want potential difference. So potential difference dv is minus e dr. Actually, it is a dot product here, but here we can see how to apply dot product. So suppose I want potential at this point, and I can go from infinity to that point. So you can move that charge from, or you are moving from infinity to this point. So we have to do definitely potential difference it is. So integration we have to do. So let us apply integration both side e dot dr. Let us write that. So minus, we are going from infinity to that point. So if you are going from infinity to that point, dr is going to be decreasing. So you have to write e dr. E dr is e minus dr. You can write. Okay, because dr is going to decrease. Then this minus minus will become plus, and let us say from infinity, potential at infinity we already know it is 0, right? Potential at infinity 0, and this is potential, so this is nothing but v minus 0. V minus 0 will give us v only. So this minus minus become plus. You have to integrate infinity to r. This is like 1 by kq by r square. Kq by r square. So let us do that. Kq by r square dr. So potential will become v equal to kq. 1 by r square becomes minus 1 by r, right? And we are going from infinity to r. K cube by r square becomes minus r. It should come positive. Where we have made mistake? Electric field is going away like this way, field lines, and we are moving like this, dr. Okay. Oh, I think again we have to remember this is like magnitude dot product, na? So this is magnitude of dr. This is magnitude of dr, which we are writing as minus dr, because dr itself is negative, and there is also because they are 180 degrees, so cos 180 degree gives us minus 1. Remember that it is dot product. Dot product means what? Magnitude of field, magnitude of dr. Magnitude of dr is minus dr. Note that, because dr itself is negative. So minus dr gives us minus minus plus. Okay, remember dr is negative, that's why we have to put minus dr. And then this minus 1 is coming because of cos 180 degree angle between the factors. So definitely there will be extra minus will be coming. Here is where people make mistakes, okay, because how sign are we choosing, okay. So then it will become plus, okay. Then let us do that integration. So then you get potential as kq, put the upper limit 1 by r minus lower limit 1 by infinity is going to be 0. So potential is kq by r, right? Kq by r, that is the formula for potential outside. This formula is valid for point r greater than equal to r. This is for outside point, outside. What about inside point? Also note that what at the surface, at the surface, at the surface, small r is equal to capital R, we can substitute, so V equal to K cube by capital R. What about potential at the inside? Inside. So we know that field everywhere is going to be 0, and if field is equal to minus dV by dr, and field is 0 means what? If field is 0 means V dV is going to be 0. That means default V must be constant. V must be constant. This is a very important result, because dV is going to be 0 means V must be constant. And what is that constant? So potential here, here, everywhere should be same, and that is same as the potential on the surface, because surface is also a point which is almost within that. So we can say that for r less than or equal to capital R, potential is going to be kq by capital R. And note that here also you can apply equality. So outside, of course, when you say outside, you don't have to put equality, but at the surface, this is what it is, and for inside the surface, this is what it is everywhere. So potential on the sphere and also point everywhere inside, that is going to be constant throughout the whole region, throughout the whole region. So that potential is k cube by capital R, where R is the radius of that sphere. Are you clear about that? Yes. So if I draw now the potential graph, now let us draw the potential graph, V versus R graph. Potential will be first of all constant. Potential is going to be constant throughout up to that radius R. After that, potential will decrease, and it is going to be a continuous graph, because this is straight line, dot 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 means this is at the surface. After that, it is like this. So this is a continuous graph, there is no discontinuity, it is a continuous graph. Okay, done. Then what about potential due to a uniformly charged sphere, which is an insulator, where charges are present over the entire volume? It's a very important result. We should do derivation, and you must repeat the derivation 2-3 times by yourself to make things everything clear. Okay, let us go to that spherical insulator. Spherical insulator. So suppose this is an insulator and charges are present throughout the volume the method is going to be exactly the same method of derivation, no changes. This is the center of total charge is q. Again we are going to choose some point inside, right? If I choose a point inside, what I will do, I will draw a Gaussian surface. Gaussian surface I have drawn. Let us say this radius is small r. So r less than capital R. For inside point, let us do the calculation. Inside point, inside points. So apply Gauss law. Integration of E dot dA is equal to charge inside by epsilon naught. E dot dA, E is constant everywhere because it's a symmetric, but directions are radial. So everywhere, if you try to see, field direction is like this way. A small area vector direction is also in the same direction. So E dot dA, when you do, E comes out, you have to take integration of dA. This is always going to be same, particularly for sphere. Okay. Charge inside is volume charge density into the volume of this. Volume is 4 by 3 pi r cube divided by epsilon naught. And now you know volume charge density means total charge by total volume. So what is volume charge density? Total charge is spread over a volume of 4 by 3 pi r cube. This is what is volume charge density. Now we'll use that. So total charge by 4 by 3 pi capital R cube into 4 by 3 pi small r cube divided by epsilon naught. 4 by 3, 4 by 3 gone. Very simple calculation. Q small r cube by capital R cube into epsilon naught, right? Okay, and here what is the area? Area of this sphere Gaussian surface is 4 pi r square. So after simplification, what do we get? What do we get here? R square, R terms get cancelled. So E comes as 1 by 4 pi epsilon naught. You can write as small k q r by capital R cube. This is the field due to sphere for points inside. Remember, this result is true for points inside, right? We can apply this. What about points outside? Same manner, do that. Gaussian surface. Do not forget Gaussian surface. You have to now choose a Gaussian surface like this. Okay, for points outside. So let us say that you have chosen a point here now. Now this is the no, we have to choose on the Gaussian surface. Okay, so you have chosen this as the Gaussian surface. This is the point P. This radius is R. So now you are doing the same calculation for R greater than capital R. Apply that. Now only thing is that charge inside will be the total charge of this sphere, because the Gaussian surface is outside the distribution of charge. So it will include the entire charge, right? So this calculation, you don't have to calculate charge inside, right? So do that calculation. What do you get? This step up to here, it will be same. So E into 4 pi r square is going to be what? Total charge inside the total charge by epsilon naught. So I am just skipping some steps, okay? You can understand that. So electric field is coming as 1 by 4 pi means k q by r square. This is like a point charge, like a point charge, like a point charge. Okay, that means field outside is like a point charge. That is what is cell theorem. Now we know already that. So field outside a solid sphere or a cell, doesn't matter what it is always going to act like a point charge concentrated at the center of that. Okay, so we have got this. Now what about at the surface? At the surface means small r is equal to capital R. Okay, this point was for outside. This was for outside. What about at the surface? At the surface, when you are doing at the surface, we will have r is equal to capital. So you can substitute either here or there. You will get the same result, kq by capital R square. Now you can see that this is going to be a continuous graph, and you can draw the graph. You can draw this graph, E versus R graph. How will this graph look like? This graph will look like, you have already seen this graph, but again I am drawing this. It will look like this. Okay, so here This is the surface r equal to capital R. This is a straight line. You remember tan theta we have also discussed. This tan theta is the slope of that graph, right? So tan theta, which is the slope, is equal to k cube by r cube, k cube by r cube, and this is like inverse relationship k cube by r square. And at this point, this is k cube by capital R square. Are you clear about this? You have already done this one. Yes. Yes, Satres. Are you clear about these derivations? Okay. So today I think we have covered all the important, but still the potential derivations are not done. Potential derivations can also be done in the same manner by the same equation. What equation? What equation? Same. Electric field is minus dv by dr. So you try that derivation. Next class we will do the derivation of this. Okay. Then this topic and questions. Try to work out questions on this. And as far as possible, focus on your next exam, your school exam, which is going to happen. Okay, whatever the syllabus is there, and you also have books right in your school materials, please work out all the questions of that related topics. Almost, work out as if you should be completely thorough with that. All the important concepts should be very much clear. If you want to repeat 3 4 times, no, the concept, the formula, the all the things, repeat it, no problem. Because if you want to go fast, means you should know everything, all the important formulas, all the important results we should know. After that, only thing that you have to do is to do the calculation correctly. Okay, so better practice all writing all the important formulas, all the important results, all the important points, write it again and work out all the important problems, and definitely you will be able to score very good marks. You need to just improve your speed. And also, if you are not sure and it's a difficult question, you can definitely skip that. No need to waste any time there. Okay, clear? Okay, fine. Then we'll see next time. Up to this much we have done today. Thank you for your attention. Yeah.